Yep. Okay. So SHA-1. So we have a string, which is really a bunch of numbers. We have it in binary. Okay. Yes. The first step is to initialize 5 random. Okay, so first, what are we going to be doing here? What we're going to be doing is, I'm going to put the function here. I don't know what the so SHA-1, I'll just say SHA-1 takes a message, right? That's what we're doing at the end of the day. It takes a message. Okay, so we take our message. Max length is 2 to the 60. By feeding a message as a bit string of length less than 2 to the 64 bits. That's okay. Less than 2. I'm not even going to check that because I'm never going to be passing a message that's that big. 2 to the 64 bits. What is that, 2 to the 64? Yeah. Right, 2 to the 64 bits, right? Which is this many bytes. So we could just check if it's... So 2 to the 64 minus 1 is the max value of a 64-bit integer. I don't know if I need to check this. My messages are never going to be that long. Length less than 2 to the 64 bits. If it's more than 2 to the 64 bits, that means the length is going to be less. I can't even represent that as a... Okay. First step is to initialize 5 random strings of hex characters that will serve as part of the hash function. Function. All right, so we've got this. We've got our SHA-1. We take in a message. Five random strings. Why are they doing strings here? Initialize 5 random strings of hex characters. Are they really random? That will serve as part of the hash function shown in hex. So they're showing this in hex, but these are really, I thought these were actually, I thought these were actually, wait a minute, it's, yeah, 32-bit integers, 5 32-bit integers. I thought that's what these were. Why are they saying random strings of hex? The message is then padded by appending a 1. Okay, so we have our ABC in binary. Okay. The message is then padded by appending a 1. Is this too small? That's okay. The message is then padded by appending a 1, followed by enough zeros until the message is 448 bits in length. Okay. The length of the message, represented by 64 bits, is then added to the end. So the length of the string. The length of the message, represented by 64 bits, is then added to the end, producing a message that is 512 bits long. Okay, so we have the whole message. Okay, what they're not saying there is that if it's more than 512 bits, you break it into 512-bit chunks. So basically, you're reading all these instructions are a bit different. Append the bit 1 to the message. Example, by adding this if message length right, okay. By adding a 1 and then a bunch of zeros. If the message length is a multiple of 8 bits. Append K 0 to 512 bits 0 such that the resulting message length in bits is congruent to minus 64. I don't understand. Is congruent to minus 64 equals 448 mod 512. Append ML, the original message length in bits, as a 64-bit big endian integer. Thus, the total length is a multiple of 512 bits. Process the message in successive 512-bit chunks. Okay, so you have a message, whatever size, you append a 1 to it, and then you add zeros such that the resulting message length in bits is congruent to minus 64, which is 448 mod 12. Again, I don't know if I need to worry about that because my message won't be more than 512 bits. Is congruent. Reaching a certain value called the modulus. Clocks wrap around every 12 hours and the hour number starts over at 0 when it reaches 12. We say that 15 is congruent to 3 modulo 12. Written, okay, 15 equals 3 mod 12. So that 7 plus 8, which is 15, equals 3 mod 12. This is really getting in the weeds here. Given an integer n, call the modulus. Two integers a and b are said to be congruent modulo n if congruent modulo n if n is a divisor of their difference. That is, if there is an integer k such that k times n is a minus b. Okay. So back to this, they're saying such that the resulting message length in bits is congruent to minus 64, 448 mod 512, which means negative 64 minus 448 is divisible by 512. So you add a 1 and then you add a bunch of zeros to the message. All right, append to 1 bit and then again, I don't think we need to worry about this. Append ML to the original message length in bits as a 64-bit endian. I think I understand that up to this point. Okay, so we have this message. We add a 1, and then we add enough zeros so that the length is 448. Now, if the message length was originally 448, then I think you'd still add a 1. Then you'd have to add a bunch of zeros so that you have. Isn't this just another way of saying that it's divisible by 512 equally? So is that what they're saying here? So that everything is in a 512. Okay. So I'm not going to worry about the size being great. I'm going to assume the size is less than 512. We're just going to add a 1, and then we're going to add a bunch of 0 bits. But I still don't know how we're going to represent this here. We're going to have a string. We're going to add a 1 and a bunch of zeros. And then the length, the original length of the string in bits, how many bits the string length was, we want that number as a 64-bit number. You add that to there as well. So now you have 512. So now you have 64 bits. And then in this case, for example, we had 423 bits, and then we have a bunch of this. How am I going to represent that? And this whole thing is 512 bits, which is how am I going to represent that? Wait, okay, so this whole thing is 512 bits, which is 432-bit. No, wait. 2 is 128, and then 4 is 250, so it's 8 32-bit integers, or 4 32-bit integers, right? So this will have to be held by, it makes sense to do it by 64 bits because this last one is a 64-bit integer. So if you tack this one on, and then you have, is that right? Yeah. 8 64-bit integers. So if we have so that's a 64-bit integer, and then the rest we have to hold as 64-bit integers. How the hell am I going to represent that? Okay, so now you have a 512-bit. Let's assume we just have one. bit long message. I understand what's going on so far. The padded input obtained above M is then divided into 512-bit chunks, and in our case there's only going to be one chunk, and each chunk is further divided into 16. Right now, yeah, why did I say 4? If it's 8 or right, it's I'm confusing myself here now. Right. It's 8 64-bit numbers, integers, or not 4 32-bit, 16 32-bit integers. So we're not going to have multiple chunks. We're only going to have one chunk, and then we need to then break this chunk, divide it into 16 32-bit words. So basically the whole message is just a bunch of 32-bit words, W0 to W15, right? There's 16 32-bit words. In the case of ABC, there's only one chunk, as the message is less than 512 bits total. For each chunk, so we can represent this thing as an array of 32-bit integers. This is going to be a pain because actually breaking this thing up, because each char is just 8 bytes, so there's going to be 4 of them per. Well, no, it'll actually evenly divide in there. Yeah, each word is 32 bits, which will have 4 bytes. So we can put 4 characters of the string in each one. And then the 1 and the 0, that's easy. And then the last one, the length of the string, that's just going to fit into two 32-bit integers. But the number has to actually carry out. So yeah, I could just have it as a pointer to the first integer and then just cast it to a 64-bit pointer to an integer, a pointer to a 64-bit integer, and then just write that out, and it will just overflow in there. That should actually be pretty easy. Each chunk. Okay, let's get to this point where we have this actual, where we have these words. We have a chunk of words, of 32-bit words, 16 32-bit words. Let's get to this point at least. So, okay, we have our message. So I'm going to want to have, we could do it as a vector. So yeah, if I had my other app, I could just do this. I could just do this, but I don't. Okay, so I'm gonna call it W, and we have 16 of them. So W, we have 16. Now let's take this message. Let's assume we could just break the message down into a single chunk. So how do we do that? Actually, wait a minute. I may have to do this. I may have to break it up into chunks. Okay, so the message size. Okay, so the message size is each char is 8 bits, right? And this WebSocket. We're taking this as an example, right? Plus this thing, right? Which is this whole thing. How many characters is that? 60. So if we have 60, okay, so that's going to be 480. So I think we're guaranteed that that's a fixed size. This thing is a fixed size. This magic number is a fixed size, and this should always be the same as well. So we should always have a 480 bit input. And so because we have a 480 bit input, that'll be fine. So how many integers am I going to take? So we're assuming that it's already a 512-bit chunk. We'd have to break it down into these pieces. So we're going to read the chars from the string to give us that. I could just have it hard-coded, or I could just do a loop. So basically what we're saying is W at 0. So like we're gonna say the message, the first character, well that's just 1 byte. So you're gonna have that guy and then that guy and that guy. So you're gonna have this. You're gonna have this bit shifted to the left by 24 bits. Right, we're gonna take our message, which is this 8, 16, 24 bits. So that message goes there, and then we're gonna OR that with the next char. That's gonna be bit shifted 16 bits, and then the next character, and then the next character is just as it is. So that's going to be our first 32-bit integer. Is going to be that guy. No, that's wrong. That guy, this guy should be bit shifted 8, and then we have the message 3. So that's the first word. Yeah, I could do a fancy loop that figures all this out. I might not. I might just. Well, how many integers is that going to take? So if we had 60 character string. 60 character string. Divided by 4 characters, that's 15 characters. So that would only leave 1. Oh man, we're gonna need to do it in 2 chunks. Shit. Yeah, we're gonna have to do it in 2 chunks. Oh, right, it's 480. Yeah, it's 480. So we're gonna do 480. So what do I do? Yeah, that's the thing. What do we do in this case where the message is... Okay, well let's just implement the algorithm as it is, and then we can worry about the fact that we're going to have to break it into chunks. Is then divided into 512-bit chunks. But okay, I don't understand what you do when the message is longer than 448. If you can't append the 1 and the zeros to get 448, what are you doing then? Wait, I might be thinking about this wrong. I'm thinking about doing that for each 512-bit chunk. I think what you do is you take... No, what you do is you take your message, whatever length it is, you add a 1, and then you add enough zeros so that the message... I think that's what they mean by... So that the message, the total length is going to be... And the reason why they say minus 64 here, I think it's because you're going to have that 64-bit integer at the end is congruent to minus 64 is 448 mod 12. So you want to be able to divide it into size 512. Given that you have this at the end. So you're going to have your message length, you're going to add a 1, and then you add enough zeros so that you add enough zeros such that your message length plus 1, this guy here, plus 64, plus that number of zeros is going to be equally divisible by 512. I think that's what that means. Once you have that, and you've got your message, you've got that stuff in the padding, then you just break that message up into 512 chunks. So sometimes you're going to use all of the message characters, but then at the end on the last chunk, well, no. Yeah, sometimes you're going to use the character. That's where it gets complicated. Sometimes you use the characters, sometimes you're going to use those padded bits. So I think you could just yeah, I'm not sure how to do this. First, let's just do the hashing of the 512 thing. Let's just worry about the 512 chunk, and then we can go from there. Okay. So let's get back to this then. So we have our message. We're going to read the first 4 characters from the message, put it in there. And I mean, this is, yeah. This is going to be the same for this, right? This is going to be a 1. This is going to be a 4, right? 5, 6, 7. So we're going to do this. Let's assume that the message... Man, I don't know how I'm going to do this. Yeah. Because Well, but this is pseudocode. This is pretty. It's actually not too bad. It's actually not too bad. Okay, well, let's see. Can you fit everything in one chunk? You can fit everything in one chunk if, because it's saying k greater than or equal to 0, less than 512. So k can be 0, so you can have no 0 bits. So what's the longest you can make it such that so you can check if that's the case. If that's the case, then you only have one chunk. If not, then you're going to have more than one chunk. So yeah. We've got our words, and we need to put, basically we're just taking our message and putting it into those words. And then that stuff is just at the end. Well, okay, we're just taking words and putting it into, we're taking those characters and just putting those into those words, putting it into those buckets. Until you get to a point where you add a 1, then you're just adding zeros until you get to the end where you add your last thing. So we just need to know, how do you know when you get to that point? So what does that look like here? We're going to be right. So if it's over, then you're actually just going to read all characters into all of the words. Do stuff, then you're going to come back in the loop, and you need to remember where you were in the, we need to keep track of the index in the message that we're at. So we're going to have an index, which we'll say is, so index, so the index starts at 0, so we start at 0, and then we're going to go 4. Well, what's the maximum number of characters we can what's the maximum number? Well, we've got 16 integers. Each can hold 4. But we're not going by, we're iterating here by each, we're doing, yeah, each one will be a word. So it's for each word. So we're iterating over each word to fill up each word block. But you can only do it if you actually have characters left in the message. So we start at I and then we go. So how many characters can we do? We have 16. Each one we can do 4. So we can do 64 characters. But okay, so no, so it's 16 words, right? So this is I. So we iterate over each word, and at each word we're gonna fill that word up. So we start with the first word. We take that information from the message. So no, this isn't index. This is 0. Index is where we're at in the message. So it would be index, and then it would be index plus 1, and then index plus 2, index plus 3. The index is plus 4. Right? I think that's what we do. So the index plus 1 plus 2 plus 3, and then we do plus 4. That's the next index that we're at, and we do that for each word. So you start with that word, second word. So we go through all of the words. So that takes everything out of there. That's great, but only if we're filling it up with the message. What if we're not filling it up with the message? So what? Okay. Each of these chunks is just going to be all characters from the message, except for the last 512-bit chunk, right? So it's going to contain this. So there's 16 32-bit integers. So 2 of those are for the end here, and then you're going to have this stuff. And so, but that padding could span. Okay, so the maximum number of zeros you can have is it's got to be it's less than 512, right? The maximum you'd have would be less than 512. K would be less than 512. So if you had 512, so 511 zeros. Okay, what's the maximum number of bits you can have here then that would still fit in the word? So you have 16. So you have 512 minus 64 bits. So that leaves 448 bits. Okay, no, so those padded zeros could span the last 2 chunks, right? Because if you have 511, hold on, you have 512 bits minus the 64 bits. So that leaves 440, right, they already have that here. That leaves 448 bits here. And the maximum number of zeros you could have would be, so in the worst case, you have the maximum number of zeros, which would be 511 bits, 511 zeros, plus that 1, so which is 512. So you'd have 512 minus 448, which would be another 64. Okay, so what you'd have is either you have one chunk or you have more than one chunk. And if you have more than one chunk, the last 2 512-bit chunks, well, the last one will have this 64-bit number here. And then you could have all zeros, and then in the previous chunk, another 64 bits of zeros and then a 1 and then the message. So you could have the message and all the chunks, but then the last 2 chunks are going to have that information. So the question now is, so I iterate over the words and I'm pulling that data from the message, but now I need to know, when do I not do that anymore? Well, you know when to stop doing that. When you no longer have characters in the message, then you stop, right? And once you no longer have characters in the message, then you add a 1 and then you pad with zeros. And the question is just, how many zeros do we pad with now? So basically, so long as you can still fit that 64 bits, you're good. I gotta draw this out here. So word 0. So you have a bunch of words. The last 2 words are going to be needed for, so W15 and W14 are going to be needed for that length of string, right? So basically, once you, so you're putting you're reading the characters in, and then when you're reading all the characters in, if you can, then you just fill it all up and it's all filled up with characters, that's fine. But then once you get to a point where you're out of characters, so you're at the last character, we then check, well, do we still have another 2 words free? So basically, if you're, depends where you are. If the last character you put filled up the last one there, then there's no room. We aren't going to put that because we have to append a 1. So we would append a 1. We would append a 1 here, and then this would all be zeros. And then we'd have to go into another frame, which would just be zeros, and then that. So if your last character was there, so we can't really do it this way because I think we have to go one at a time. We have to put 1 in at a time. So WI if we just say that guy bit shifted to the left, I think we have to clear it, right? I think we have to say, so WI is 0, right? So WI is 0, so it's all cleared of zeros. And then WI is 0. And then well, no, do you need to do that? So you say message at whatever index, that char, which is 8 bytes, bit shifted to the left by 4, that gives you a 32-bit number. So I think it's that. '24. So you're gonna put that guy in there. This could just be another for loop though, couldn't it? Right, in a word, we're filling in 4 characters. So on j is less than 4. So we say, so W, I, yeah, so in that case, we do have to say WI is 0. And then WI is equal to the message at whatever index we're at. Index that we're at, and then increment the index. Bit shifted to the left. 2 to the power of bit shifted to the left, j times 8. Right? Wait, no, we do. Yeah. Is that right? So we clear it, it's at 0. Then we say message at the index, which is 0. Then we increment it. Bit shifted to the left by, so it'll be by 0. Then it'll be by 8. Then it will be by 16. Then it will be by 24. But I need to go back here to here. This is actually ORed. So WI is itself ORed with this. And that's why we clear it to 0. That's why we clear it to 0 here. Because yeah. OR it, and then OR that, then OR that. Okay, so that will work. So that'll pull the characters out from the string into there. Now we're gonna keep doing this for all of the words until if we get we stop when we run out of we keep going until we don't have any more characters left. So if we fill up the words, we fill up the words, we have our block. If we don't fill up the words, so if we do run out of characters before, so what we then check is, so that's the next index. If the index is that, so we don't have anything left. So the next time we come back here, we check if the index we check if the index is equal to message dot size. If the index is equal to the message dot size, we break. We're not going to take anything out from the message anymore. Right? So if the index is equal to the message another way of doing this, maybe just if the index is less than the message size, so if the index is less than the message size, then we're good. We do this. Otherwise, if it's not less than the message size, so then we stopped. Now we need to know, can we just fill up the remaining with the end or not? Like, do we put stuff in the end 32 bits or not? and 64 bits or not. So if it's less than that, yeah, how do we know that? So if you're here, you wouldn't have room because you're gonna need another 1 bit. Basically, is there gonna be enough? Are there 64 bits plus 1? So are there? You need to ask. Are there 65 bits left? If there are, then you're good because you can then. We're good because we could put the one and then the other 64 bits for the length, and we're good to go. We don't need padding if we don't need it. If we don't have 65 bits left, then we don't have enough to write that last 64 bits of the message length. So we're just going to put the 1 and then pad the rest with zeros, and then in the next message we'll continue padding with zeros and then do that. So do we have at least 65 bits left is what we need to ask. So when we get here, so we don't have any more characters left in the message, we need to ask, do we have at least 65 characters left? So maybe that's in here. So how do we know how many characters we have left? Well, we know which word we're at. We're at word, so this is like... We know which word we're at, and we know which... So we've filled this in, we filled this in, we filled this in. Now we're at the next... integer block in this word. So how do we know how many bits we have left? Well, we could know how many bits we're in. So this is, each of these is 8 bits. So this is going to be bit 0. How many bits? Well, which bit position, how many bits have we written so far? That's what we can check. Well, the number of bits we've written is just I, which is the index of the word. Each of those is 32 bits, so I times 32. So we do I times 32. So let's say it's that one. Then that would be 8 bits, 16, 24 bits. So there would be 8 bits remaining here. So if I is 0, if that's 0, then you did 0 times 32, which is 0. So I times 32, because each of these is 32 bits, plus, well, we could say the size of I times the size of int, but really, yeah, it should be 32. So I times 32 plus your offset in here, which is j times 8. So that's how many bits we've written. All right, so if you'd be this one here, that would be 32 bits plus 8 bits, which is 40 bits. So we've already written 40 bits, so how many are remaining? So the number remaining is the total size of this thing, which is 512 bits minus the number of bits we've already written. So minus I times 32 minus j times 8. And then we check if this is greater than or equal to 65, right? This is how many bits are remaining, right? 512 minus I times 32 minus j times 8. That's how many bits are remaining. Just to make it easier to read that, I'm just going to do this. This is how many bits are remaining. So 512 minus 132 minus this. If the number of bits remaining is greater than or equal to 65, then we're good. We have enough for the message length plus that 1 bit. So then we could also write or else so if not, let's look at the case where it's not first. If not, so if we don't have at least 65 bits left, do we have to do it that way? And we don't have to do it that way. Yeah, we don't have to do it that way. We can say, I think this is way more complicated than it needs to be. Instead, we could just say, well, what's the last position you can be at? You need 2 more words plus 1 bit. 2 more words plus 1 bit. So you'd have to be here. So if I is less than, so if I is less than 14, if we're not at the 14th word yet, and if j is less than, we can have written 0, 1, and 2. Right, so we write 0, 1, 2, and like let's say that's the last one. Then we get to 3. At 3, we don't have a message. So if j oh no, that's it. If I is less than 14, that's all we have to say. Okay? If I is less than 14, then we're good, because it doesn't matter where we are in that word. Even if we're writing to the last 8 bytes, that's where we're writing to next, we're good. So if I is less than 14, we're good. So let's assume, okay, if I is not less than 14, then what do we do? So then we're in the 14th word. What are we doing on time here? 1 hour. Okay. If it's less than 14. Good. Okay. If it's not less than 14, then that means we're in somewhere in here. So we can't write it. So we're going to have to push this into another chunk. So what do we do? Well, we need to know, are we just padding with zeros or... No, we don't have the message anymore. I'm just going to keep track of whether or not we have added 1. padded 1. So again, I'm violating my own. I'm trying to change padded 1. I want to change my naming convention. So padded 1. So if we haven't padded a 1 yet, then padded 1 is true. And we're gonna say, so WI, we OR it with, well, we're just gonna put a 1 wherever we're at here. So we're gonna put a 1 at the end. So we're gonna take the 1 bit, shift it over how many times, and then if we didn't pad a 1 yet, then we're gonna do that. Padded 1 is true. We're gonna take the 1 bit, shift it over so that it's all the way to the end. So we're gonna shift it over 7 times. So WI is gonna be ORed. So let's say we put this one, we put this one, we put this one, then we get to here. It's gonna be bit shifted. No, that's not right. It's gonna be bit shifted 1, and then we're gonna shift it over. It's gonna be bit shifted 7 times J. Seven times 3 minus J. 7 times 3 minus J. Is that right? So if J is 3, then it's going to be no. We want that to be 4. So 4 minus 3 is 1. We're going to bit shift it 7 times, right? If we're at the first one, so J is 0, then it's going to be 4 times 7, which is, we should be shifting it 8, 16, 24. Wait a minute. When it's 3, we should be shifting it 7 bits. When we're at 0, we should be shifting it 24 plus 7, 31 bits. Right? And then when it's 1, we should be shifting it 16 plus 7 bits. So 7, 31, 23, and then 15, right? 8 plus 7, yeah, 15 bits. So that's you do you do 4 you do I times 8 minus 1. right? When it's 0, no, you have to do, you do 4 minus I times 8 minus 1. So then you have 4 times 8 is 32, minus 1 is 31. For 1, you do 3 times 8 is 24, minus 1 is 23. 3, you have 4 minus 3 is 1. 1 times 8 is 8, minus 1 is 7. That's right. So that's, or that's 32 minus 8i minus 1. Or it's just 31 minus 8 times I. Right. 31 minus 8 times I. Right? 31 minus 8 times I. I'm going to do I times 8. Okay. So we now have a 1. We've bit shifted it to that position. So now we have the 1. The padded 1 is there. Now, if we've already added the padded 1, what are we doing? Well, okay, so we cleared W, we've cleared it to 0, and then we OR'd all of our stuff in there. We actually don't have to do anything anymore. Once we've added the padded 1, we actually don't have to do anything. If padded 1, then padded 1 is true. I don't think we have to do anything. I think we actually just break out of this for loop. Right? We add the 1, and then it's going to be zeros after it anyway. So now we're done. We've added our 1. That marinating block has zeros. The rest of this word is all zeros. So we break out of this for loop. And then we would go to the next one. We then go to the next one. And you get to the next word, it clears it to zeros. It's already doing that for us. Then we check, well, no, we don't have any of the message left. We won't have any room left. No, we don't have any room left. If we don't have any room left at the beginning, we won't have any room left afterwards. And so, and the padded one will already be there. So just it'll iterate over all the year, just waste time because the padded one will already be there. If not padded one, we could yeah, we could just say we could do this so that it'll come in here. If we don't have a padded one, then we put a padded one on there. And then padded one is true, and then we break out. Once we go to the other ones, we come in, no, we won't have enough room. We already have a padded one, so we just break out. So we just leave the rest as all padded with zeros. So I think that's good. If we're here, this will all be left with zeros, or if we were here, we do that. And then all the subsequent ones will be left with zeros. You're not going to have room, right? If I wasn't 14 there, I is only going to keep getting bigger, so you're not going to have that problem. Okay, I think that's good. Now, how am I going to test this out, though, to see what we're looking at? Okay, so let's go back to here. So that's good for that. That'll grab everything from the word and then pad it. But actually, let's call this function from here then. So what we're going to be doing here is we set the status code, we set the message. Now we want to add a header. So response.headers. We just add a header. What is the header that we're adding? Sec WebSocket accept. So sec WebSocket accept. This header is going to be this thing. I'm just gonna call it hash for now. So yeah, it doesn't matter. We're not even gonna get to this point for now. Just want to make sure I name that right. Sec WebSocket accept. Yep, sec WebSocket accept. Oh, here's another check we didn't make. Right? Or what is it? Sec WebSocket key. No, because do we still have our function? I hope we still have our function. Not has header. Not has header value, but has header. Sec WebSocket. Is that what it is? WebSocket key. Okay, I do still have has header. And sec WebSocket key, yeah. Okay. So if we don't have a sec WebSocket key, then that's a problem. If we do have a sec WebSocket key, then what we're going to be doing is we're going to call, for now I'm just going to call SHA-1 and request.headers sec WebSocket key. We know that we have it. We're just going to pass that in there. What we would actually do is we would take this key, do this stuff with it, and then set that in the response accept. The response.status code. So maybe I'd move this stuff over. So we would do this stuff, and then we would be done, and we would set our hash here. So But okay, that's what we would do, I think. But for now, let's not do that. For now, let's just call SHA-1 and let's pass in something that we actually can test. They have an example here. So the quick brown fox jumps over the lazy dog. We're gonna do that and see if we're getting the right. Maybe. Let's do this one. Let's do ABC. Let's do ABC. So that's what we're doing there. Okay. So set a breakpoint there. The problem is though, for this to, okay, now I don't want to have to make an HTTP call just to call this. So, yeah. Let's go down to, let's just do it here. So, boom, we get to here. Our message is ABC, that's right. So, we have our word, which is just a bunch of garbage. We clear it, we come in, extract the information. There's 3 of them, that's correct. Okay. Let's just see if I had it right up to this point. So I'm just gonna grab this and see what's going on here. So W should be, I want to see it in binary. There's a hex display. All right, so we only have 3 characters, so we're only going to fill up the first word. That's correct. So we're still in the first word. We filled up the first word so far. This looks okay. How can I do this here? Type var b in the wash for binary. Oh, okay. So if I could say WB. Can I say W1, W0B? Yep. Okay, let's see if this looks correct. So wait a minute, it's off because so I have 0, 1, 1, 0. Okay, let's run it again. So we add our first one. Yeah, that's wrong. Unless it's showing it. Oh, is it showing it opposite? No, that's right. It's 0, 1, 1, 0, 0, 0, 0, 1. That's right. That's A. But this should be this should be bit shifted. Why isn't it bit shifted? Oh, because I did it wrong there. So I'm bit shifting. I'm bit shifting wrong here. It's not J times 8 because then J is 0. What I could just do is go backwards. I could have J go from 3 down. Maybe that's what I'll do actually. Yeah, maybe that's what I'll do. So you want to go 3, 2, 1, 0. So J is going to be 3 while J is greater than 0. What is happening here? Okay. There we go. Now you have 0, 1. Okay. Now we get the next one, the next one. So now at this point we have 0, 1, 1, 0, 0, 0, 0, 1. And then we have 0, 1, 1, 0, 0, 0, 1, 0. And then we have 0, 1, 1, 0, 0, 0, 1, 1. That's right. And then all zeros of the rest. That's correct. So then we should just add another 1 at the bit here. So let's do that. So we get in here. If we don't have room, then we just pad it with the 1 and then the rest is all zeros. If we do have space, so when we do have the case where we have space, so let's say we did the 1, we padded with zeros. What do we do? If I is less than 14, so if I is not less than 14, then we're just going to put a 1 and then afterwards it's all zeros. In this case, it is less than 14. So what do we do? I think we do the same thing. We check if we aren't padded with 1s. If we aren't padded with 1s, then we do the same thing. So we put a 1 there. Padded 1 is true. Okay, so we put a 1. And then that's it. We break out because we want the rest to be zeros. Right? If I is less than 14, then we do this. Wait a minute. If I is less than 14, yeah. Break, right? So we'll add the 1. Then we break out, the rest is all zeros. So then we're going to go to our next word, right? We break out, so we're going to go to our next word. So if we had here, we break out, we go to the next word. At the next word, we would check we don't have any characters left in the message. I is less than 14. We still have room. We haven't padded, we've padded a 1 already, so we do nothing. It's all zeros. Then eventually you get to I is equal to 14. So if I is less than 14, okay. If we need to do another check. We need to actually say if I is equal to 14, right? If I is equal to 14, so what we'll do is we'll put the 1, we'll pad this with zeros, we'll pad this with zeros, and then once we get to 14, we can add the last thing in. If we weren't at 13, if we were at 14 when this happened, so we run out of message, I is not less than 14. Is I equal to 14? Yes, I is equal to 14. We then check, well, did we pad a 1? If we didn't already pad a 1, then you can't do anything. If I is equal to 14, then we check if we didn't pad a 1. Either way, we're going to break. Regardless, we're going to break, right? Regardless, we're going to break. So if it's not 14, if I is less than 14, then we're going to do this and pad with zeros. Wait a minute. Okay. If I is less than 14, we do this. What were we doing? If it wasn't less than 14, then we put a 1. Right, if you were here, we should check, do you have a padded 1? Is I less than 14? Yes, then we do this. Once this isn't the case, so you're at the 14, either you're going to keep going or you're going to stop. If it's equal to 14, then we check, do we have, we check if is I equal to 14. If I is equal to 14, now I think what we do here, if I is less than 14, we do this. If it's not less than 14, else, then we check, do we not have a padded 1? If we don't have a padded 1, then put a padded 1, right? Boom. So we get to 14. If we don't have a padded 1, then we're going to put a padded 1, and then we're going to keep going. So padded 1 is true. Then we're going to break out. Then we're going to go to 15. We already have a padded 1, so we don't do anything. If we don't have a padded 1, then we do this. If we have a padded 1, then we check, is I equal to 14? Because if I is equal to 14, then we're at 14 and we already have a padded 1. So we can actually add the rest of our stuff now. Right? If we don't have a padded 1, then you put the padded 1. Padded 1 is true. And then we break. And then we'll go to 15. We have a padded 1, but we're not at 14. So we clear that one as well. So if I is equal to 14, then what do we do? Then we've already got a padded 1. So now we're just going to write the last information that we need. And the last information that we need, I've got it on my other screen here. The last information that we need is the length of the string. We need to know what was the original length of the message in bits. So that number as a 64-bit number. So I think the way we can do that is we could say I think what we can say is we can static cast to a long, a 64-bit integer. So static cast to a long, static casted as a pointer to a long, is it? Static cast as a pointer to a long W14. Right, so W14 is a 60, we're going to pretend it's a 64-bit integer instead of a 32-bit integer. So, right, so W14 pointed to that guy, static acid to a long pointer. And then we would dereference it. Is that what we're saying? We would then dereference the pointer and say it's equal to the message length in bits, which is the message.size. This is how many characters we have times 8. Is this correct? I think this is right. Okay, and this actually will chunk stuff up for us too, because we keep track of the index, and every time we come back, padded is false. Okay, let's run it. Why can't I do this? Is it saying I have to do static cast to a pointer to a long? Why can't I do this? Oh, do I have to do reinterpret cast? Is that why? Reinterpret cast? Yeah, okay, so I have to do reinterpret cast. Okay, so I'm just gonna pull up this as a reference here. So we go through, let's take a look at that, this guy here. We go through, we have our, okay. I wanna pin this here. Okay. Write that, and now what? Do we have enough room? We should have enough room. We absolutely should have enough room. So now what are we gonna do? There should be a 1 written to this bit here. Yes, no, we're gonna do this. It didn't add a 1 there. Why didn't it add a 1? I is 0, so it should be 31. I don't think my math is right about that. I think I fucked up the math there. I'm doing I times 8, which is 0. No. This shouldn't be I. I think this should be J. This should be J. So come in. We have our first guy. We have our second guy. Third. excuse me. We should have a 1. We don't have a 1. Okay, what am I doing wrong here? The math was working out. Oh, because I flipped the J stuff. That's why. J is now 3. So now this is flipped. So, so now when the first one you're at is actually 3. So it's actually, it's J. It's J times 8 plus, wait, yeah, J times 8 plus 7. Is that right? Here your J is 0, so you're going to have 7. Here your J is 3, you're going to have 24 plus 7. I think that's right. What's it complaining about you? I don't know what the complaint is. Overflow. Using operator star on a 4-byte value, then casting the result to an 8-byte value. What the hell, man? Can't we just say, okay, hold on. Static cast this to a long. Does that resolve this? We're all zeros. Boom. We put our first one. We put our second one. We put our third one. We come in here. This bit should be 1. Giggity. It's a 1 now. Breakout. Now we look at W2. So W2 is cleared to 0. And so we just break out. And W3, we just break out. W4, we just break out. It's going to do this until the last... It should do this until the last 2... I'm just going to put a breakpoint here. I'm just going to put a breakpoint there. Locals, let's pin it. Right, and that's what it's doing. We have this number, and then we have all zeros here. We're clearing everything. Now we're at 14. We have it padded at 1, yes. So now this is the true test here. I want to see what's happening at W14. I know this might be really small. This might be really, really small. But, well, it is what it is. And it isn't what it isn't. Okay, okay, this should work. So we should be seeing, this is the last one. It's all zeros. Yes. Boom. That's right. That's right. So this looks like the correct binary chunk that we have now. So this was just one single chunk. This looks correct. And the thing is, we can now handle multiple chunks because it's going to do this. If it's only going to use the message, it will go through. And when we come back here, when it comes to do this again, it will then end. Right? It will then end. So when you come back here, we check, is the index Do we still have characters? If we don't have any characters left, no, what we want to do here is, I think we're going to have to say done. Last chunk. I think we're going to have to say last chunk, and then here last chunk will be set to true. So if when we do this, we know, okay, we're done. We don't have to keep going because we're at the last chunk. Okay. So, what's our time looking like? An hour 45 minutes. That's actually not too bad. Okay, so we have our chunk, and it should work for chunking longer messages as well. But we have our chunk. Now what do we do? Apparently there's only 2 steps left. Oh no, there's a significant amount of stuff. Okay. Jesus Christ. Okay, so the padded input obtained above M is then divided into that. Okay, we're doing that for each chunk. So we take a chunk. Now what do we do? Begin the 80 iterations I necessary for hashing. 80 is the determined number for SHA-1, and execute the following steps on each chunk MN. So the nth chunk, we're going to do the following steps. We're going to do 80 iterations for each chunk. In other words, we're going to be doing this. So we're doing 80 iterations. Right, on a chunk that we have up here. So we have this W. Our chunk is the W here, 16 integers. Do I have to do this with the cast? Do I have to do this? Static acid to a long times 8. So it's this, and then set that equal. I think I do. I think I do. Okay. This is why we use C++. You can't do this kind of stuff in. You can't do this in Java. Maybe you can. No, I don't. No, you can't do this in Java. This is why you use C++. Okay. So we're like not okay. We've started making some progress here. So we've got this. We're looking like this. Now what do we do? We're iterating 80 times with this chunk. What do we do? For iterations 16 through 79. So begin the iterations I. For iteration 16, I'm assuming they're saying starting with the 0th iteration or the first iteration. For iterations 16 through 79, so where I is between 16 and 79, perform the following operations. Do we start with I being 0 or 1? Well, we're doing 80 iterations, so I'm assuming they mean on the first iteration. So the 79th should be the last one, I think. So this is the operation that we do. W are the words that we already have, so that's easy to get. I'm not sure what, I don't remember what this represents. Exclusive OR, right? Where exclusive or this is represented by the following comparison of inputs X and Y. Okay, we know what exclusive OR is, so we do this, exclusive OR this, exclusive OR this, exclusive OR this. I don't think I've ever used exclusive OR in C++. I think the symbol is what's the symbol? I think it's this. Yes, I think it is. I think that's right. Yeah, it is. Okay. I've never actually used exclusive OR. But there is no operator. No, I want bitwise. I want bitwise exclusive OR. fuck's sakes, man. Just give me the answer. Okay, there you go. Yes, that's what it is. That's exclusive or. So we do that, exclusive or that, exclusive or that, exclusive or that. And change the word I. That's for the iteration 16 to 79. For example, when I is 16, they should be clear about this though. Does I start at, for when I is 16, the words chosen are W13, 8, 2, and 0, which are these words. Okay, and then 0, so word. Okay, I can't be 0 because then you'd have 0. Okay. So word 0 is that one, for example. Wait a minute. W0 is... Yes, that's right. Yes, that's right. That's W... Okay. All right, and the output is a new word, W16. So performing the XOR or this operation on those words gives all of these exclusive OR gives this new number. Okay, that's fine, but then the question is, okay, this makes a bit more sense now. This makes a bit more sense now, looking at this. So we're iterating over each chunk. Break the chunk into 16 32-bit words, which we have between 0 and 15, right? Message schedule. Extend the 16 32-bit words into 80 32-bit words. What the fuck is that? So for I from 16 to 79, okay, I thought we were doing 80 iterations, and at each iteration we're going to do this thing. Begin the 80 iterations I. For iterations 16 through 79, perform the following operation. So an I is between this, then you do this. They're doing something different. Okay, so they're saying, so they go from 16 to 79 and they do this left rotate. I've got to figure out what this left rotation is. Initialize the hash values for this chunk. So we set A, B, C, D, E to be the original hash values here. We do this stuff to modify the word. We modify the words. So from 16 to 79, we modify the words. We do this. Then we do the loop. So we go from 0 to 79. So we do 80 iterations. And then we do this. Okay. And then the hash result is what it was before plus A, B, C, D, E. Right. And these are 32-bit integers as well. Each of these are 32-bit integers as well. So we have 5 32-bit integers. Is that right? 5 32-bit integers. Yeah, that's 160 bits. Okay, so how's our time doing? Okay, not sure how far I can get today here. But I think I'm gonna do, okay. Okay, I thought we were doing 80 iterations and that didn't make sense because this would do the same thing every time. Okay, so what we're actually doing is we're doing for I equals 16 while I is less than 70, while I is less than 80. Maybe I'll say that differently. So I is 16. So for I 16, while I is less than or equal to I don't know. Should I do it this way? (16 to 79). Okay, yeah, let's just do it this way. So what are we going to do? We're going to say W at I. So go W, the word at I. Hang on a second. What are we talking about? We have 16 words. We're saying W at I, but so I is going to go to 79. So we're going to say W at 79. I is between 0 and 15. So how are we saying W at I 16 to 79? Am I misunderstanding this here? We have 16 words. So how are we going to say W at I when I is 79? How are we going to do that? For iterations I through 79, where I is between 16 and 79, perform the following operation. Oh, this S1 is this left rotate thing. Okay, because when I is 79, yeah, how are we doing this? W at 7, like, I don't understand how we're doing this. For iterations where I is between 16 and 7, perform the following operations. Oh, we're creating new words, right? There's going to be more words. That's what we're saying. Extend the 16 32-bit words into 80 32-bit words. So I have 16. There's actually going to be 80 words. Okay, so there's actually going to be 80 words. So we're doing so we're doing 79. So this is adding 64 of them. Right. So we had 16, and then we're doing 64 iterations here. We're going to add 64 more of them here. So so W is actually not 16. W is actually going to be 80. We're actually going to have 80 of these guys, which is fine. We don't have to change any of this. This is still between 0 and 16. Less than 16. So we have 80 words. Now we're going to go between 16 and I'm just going to say, yeah, I don't know. Usually I would just say less than 80. I is 16, well, I is less than 80. 16 to 79. W at I is equal to, so we're going to do all of these exclusive ORed and then left rotate 1, whatever the hell that is. Circular shift. We'll have to look at what that is. Are they talking about that here too? Yeah, you then do this. And then there's this shift here, operation here. Circular shift operation. Okay, this is actually a really good, this tutorial is a lot more in depth than the other one. I like this. Is actually pretty good. Circular shift operation. So let's do the exclusive OR first. So we're doing exclusive OR of, we're doing W of I minus 3 exclusive or I minus 8. Yeah, but when I starts out, I is 16. 16 minus 3 is 13, which will have... Okay, it will fill them out as we go. So exclusive or I minus 8, and then exclusive or I minus 14. Exclusive or I minus 16. Right? I minus 3, I minus 8, I minus 14, I minus 16. That's all exclusive or together. Okay, that's not too bad. Now we do this shift thing. This circular shift on that. Now the circular shift operation, S and X on the word X by n bits, n being an integer between 0 and 32, is defined by, so we do a shift 1. So 1 bit shift, which is why we keep bouncing around here. Which is why they're saying left rotate by 1. So X is X bit shifted to the left by 1. Oh, it's just a left shift? Or X shifted to the right 32 minus n times. Where X is bit shifted to the left n is the left shift operation obtained by discarding the leftmost n bits of X and padding the result with zeros on the right. It's just a left shift. Left rotate. So here's a left rotate. You have this. You shift it all by 1. That's all. That's literally all it is. I think that's all it is. So we take this number. So we take this and then we bit shift it to the left by 1. That's all. Right? So you take this, bit shift it to the left by 1. That gives us that. Now we get to our... Okay, so that's that. Not too bad. So we're at this point. We do that. Boom. We do that. Okay. This is the last step here. Okay. And we're going to be able to easily test this. I'm just going to give it inputs and we see if it gives us the same output. So a left shift, where I is this, would produce... Yeah, that makes sense. Where WI is 10011, 10, would produce... Whoa. Aren't they wrong about that? This is a right shift. They've shifted this to the right. As the rightmost bit is 0, is shifted to the left side of the string. So you bit shift it to the left. Oh, so they bit shifted it to the right and then put a 0 there. So a left shift, where that is this, would produce that as the rightmost bit, 0, is shifted to the left side of the string. Therefore, W16 would end up being, so this guy here would end up being, you chop off the 0, you have 1, 1, and then you just have another 0. Okay, so I understand that. So if there was a 0 there, then you just do a left shift. So if there's a 0 here, you just do a left shift. But if there's a 1, you do a right shift by 1, and then you have, that's it. Is that what it is? So this is equal to, okay, right. It's a left shift by 1 or a right shift by 32 minus n. Or this, where x is, this is the left shift operation obtained by discarding the leftmost n bits of x and padding the result with zeros on the right. Okay. This is the right shift operation obtained by discarding the rightmost n bits of x. Isn't this a... But isn't it 32 minus n bits? I don't understand this. Is the right shift operation obtained by discarding the rightmost n bits of x. I don't get why they're doing 32 here. Wouldn't it just be x bit shifted to the right by n? Discarding the rightmost n bits of x and padding the result with zeros on the left. Thus, this is equivalent to a circular shift of x by n positions, and in this case, the circular left shift is used. I don't understand what they mean by or. So here it's a left rotation. So here if you do a left shift, it just shifts it to the left and there's a 0 there. That's fine. Okay, so they're saying this 0 went here, right? Here, it's a right shift, so you've shifted it all to the right by 1 bit, and then that 1 bit then goes here. I'm confused. Why is it or? Wait a minute, are they ORing? Is that what they're doing? They're ORing these two things? It's a bitwise OR? Is that what they're saying? Because, so you have this would produce this. As the rightmost bit 0 is shifted to the left side of the string. So you have 1 0 0 1 0. What does it say? What does it say here for left rotate? Rearranging the entries in a tuple. They say it's a left shift by 1. Right? This is a... What a great function name, eh? ROTL32, because that's very clear, right? Rotate left 32, rotate right. Why would you name it that? ROTL32... Yeah, it's taking the value, it's shifting, it's doing it right. Okay, so it's doing a left shift, and then it's ORing that with the value right shifted by the count end with the mask. I'm not sure why that is. But this doesn't really say that. This is saying... this ORed with that. Okay, let's see if that works. So you take this, so you bit shift it to the left, so that means you get 0 0 1 0 0, and then you OR that with, if you take this and you bit shift it to the right 32 minus 1, so 33 times. I don't, that's the thing, I don't really understand that part. I'm confused about this mask. So you take char bit. Size of value. Yeah, but you know it's 32 bits. You're setting it as 32. So you're doing 32 minus 1, which is 33, times char bit. I don't know what the fuck char bit is. Shift values which are not negative and smaller than mask used with bitwise n prevents undefined behavior when the shift count is 0 or greater than the width of the unsigned n. Okay. So you do the mask end with minus the count. So you're essentially doing I just don't understand. I don't know what you do if you take a number and you bit shift it to the right by 31 bits. Does it wrap around? I don't think it does. Doesn't it pad with the zeros? I don't know. I don't know. I just want to know what it's doing there. Yeah, I think what it should be, so you'd have 1, 0, 0, 1, and then the 0 would be there. And then you OR those together, you'd have 0, 1, 1, 0, 1. Yeah, 0, or wait, when you OR this together, you get 0, 1, 1, 0, 1. They have 0, 1, 0, 0, 1. So a left shift SN this, where this is this, would produce that. I'm fucking confused. I'm confused. They're saying left shift, right shift, but the whole thing is a shift. This is saying it's a left rotation. Where this is the left shift operation. And then this is the right shift operation obtained by discarding the rightmost n bits of x and padding the result with zeros on the left. But they don't actually do that. They don't actually do that, right? Here, you have this number, you right rotate it, and they've padded on the left with a 1. Is equivalent to a circular shift of x by n positions, and in this case, the circular left shift is used. I'm fucking confused. But what they're doing here, so I'm confused. I don't understand. I don't understand. I don't understand this. You're bit shifting to the right by 31 bits. But they're saying it's by 1 bit. Okay, let's just do this here. If I take so if I take 1, 0, 0, 1, 0. Wait, how do you binary in C++? 0B, right. 0B. 18, okay. If I take A, I'll say. So if you do A, bit shifted to the left, or bit shifted to the right by 31 bits, what do you get? You get 0. That's why I'm a bit confused here. What are we doing exactly? It's a left rotation. So to me, this makes sense. If they're taking this, you bit shift it to the left, that makes sense. I'm just confused about this here. I think what you're doing here is you're bit shifting to the right and then moving that one over. Oh, I did this wrong. So the number, okay, hold on. So you have 1 0 0 1 0. Shift it to the left. You have 0 0 1 0 0. Shifted to the right, you have 1 0 0 1 0. And when you OR that, you get 0 1 1 0 1. But they have 0 1 0 0 1. Is this a typo? I hope this is a typo. This should be a 1. From what I'm understanding, this should be a 1. I understand this. So this, I understand. Because ultimately what you end up having is you took this and you've... No, I don't get what's happening here. When you bit shift to the right, you lose all that stuff too. So I don't get this 32 minus n. Let's take a look. Circular shift operation. Online. Circular shift. The value is 10010. 10010. We want a circular shift. So you could do a right circular shift or a left circular shift. So a left circular shift. So a logical shift is this or this. I get that, right? Yes. Okay. And then a circular shift is a left circular shift is you shifted everything to the left and then you moved this one down here. And then this right one, you moved everything to the right and moved one down here. Now this one is a left rotation. So a left circular shift, is that what we're saying? Which does this. So a left shift, a left circular shift of 1. Okay, let's just say 5 bits here so that it's clear. Of 10010, this doesn't even match what they said. So a left shift, where I is this, would produce 01001. Okay, I'm going to go based off of this. So a left circular shift, I'm assuming what we're doing is this, because that's what they're saying there, right? So a left circular shift, which is this guy, you shift everything over to the left by 1, and then whatever was here goes over here, and it was a 0, so you have a 0. And in this one, if you do a left circular shift, you have 0. It should be 0. It should be 00101, which is what this is. 00101. I think this is a typo. I don't think this is right. I don't get how they got to that. They even have it here. Left rotation. So a left rotation, shifting it to the left and then moving that, and that's what this showed in this example. I'm assuming that's what they do then. It's gonna be hard to tell if that's actually wrong, if I made a mistake there. Okay, so let's do that. Left rotation. So how do you do that? Well, you just do a left shift, which we do, but you need to preserve that first bit and basically put, oh, I get it now. You bit shift it all to the right. Okay, I get it now. I get it now. So this is not a left shift. This is not that. What you do, we exclusive OR all that. That gives you WI, and then WI is equal to, you take WI, you're gonna, we bit shift it to the left by 1, and then we're gonna OR that with, you take WI and you bit shift it to the right by 31. So you bit shift it to the right by 31, that gets rid of everything except the last bit, and then you OR that with that. I think that's correct. Let's say, for example, we look at, can we do this as an example? I think so. So let's say we have this 32-bit number. So we have this 32-bit number, A, and then we do that. So we do A bit shifted to the left, or with A bit shifted to the right by 31. What is B? B is now this, and now if we say decimal, binary, we get this, which is not what we got. Wait a minute. Copy that. Well, almost. 1 1 4 zeros. 1 2 3 4, and then a 1 and then a 0 and then a space. Yeah. So that gives us that. Okay. Okay, so we now have that. So where are we at now? We've got this. We now extend this, so now we have 80 32-bit words. I might put a comment here. Circular shift left. Just to make it sound as if I actually... Well, I understand how it works now, but that was... I think this is a typo, and that added a lot of confusion there. Okay. Now store the hash values defined in step 1 in the following variables. So now we have A, B, C, D, E, and they're equal to the original hash function values. So I'm going to take those values. Actually, we'll put that... Okay, I'll do this. So int h, we have 5, right? H0, I could just do, I'm just gonna do it like this. H0 is, so in hexadecimal, we have 67DE2A01, BB03E28C. Two, 9, 3, E9, E2, H4, C, D, E, F, 23, A9. Okay, is that right? E2, A01, BB, 03, E, 28C, 0, 0, 1, 1, EF1DC, 9, 2, 9, 3, E9, E2, C, D, EF, 23, A9. Okay, so we have the original hash function values. Yeah. Okay, now we're gonna have, so now we're saying we have here we are, step 5. Fuck, here we go. So for the hash values defined. Okay, so now we have A, B, C, D, E. Why do we need this intermediate step here? So we do this equals that. And then H0 is equal to what it was plus A. Okay. So, okay. So we created all this, then we do our iterations. So we start out, okay. So A is H0. So 0, 1, 2, 3, 4. Okay, so 0, 1, 2, 3, 4. Now, what do we do? For 80 iterations, where I is between, the way they describe this is actually confusing. This is constant, so yeah, okay. It's confusing the way they make this. For 80 iterations where I is between 0 and 79, compute. So now what do we do? Now we do this crazy thing for 80 iterations, right? Oh, we have another shift operation by 5. I'm not sure if I should break that into an actual, I don't think I'm going to do that. Ah, what the hell? Maybe I will do that. Circular shift left. So it takes an int x and then a count. So it's actually going to be 32 minus the count, the amount that you're shifting, And this is going to be X and X, and this is count. Circular shift left, X the count, X shifted to the right, 32 minus the count. Okay, so now if we go up to here, instead of this, we can just say, yeah, instead of this, we could, it's actually kind of nicer. We can say circular shift left of this thing by 1. So circular shift left of this thing by 1. Yes. Now we come into here. So we're doing, I don't know what the fuck we're doing here. So, okay, so we're doing A plus, so for 80 iterations, so we do Wi plus K of I. I don't know what K of I is. See below for details on the logical function f and on the values of Ki. Reassign the following variables. So temp is equal to, so this temporary value is, so what are they doing in here? What are they doing in here? In here, they're just doing each iteration. If it's between here, we do this. If it's between here, if it's between this, we do this. Oh, okay. Yep. So they do this temp, and then they swap everything around, and then they keep going. Okay. I could probably just go off of this. But, so temp is this, and then reassign the following variables. Okay, store the result in the chunk's hash to the overall hash, and then update the hash and proceed to the next chunk. And then as the final step, we do one more thing, which is what they're doing here. See, there's left rotate, and then there's left shift. So there's left rotate. Maybe I should call it rotate. Circular shift. Circular shift operation. Okay, I kind of get. So we just need to figure out this function. I might call it rotate left, circular shift left. Okay, I might rename this then. I think I'll call it rotate left. That good? Rotate left. Rotate left. Left rotate. I'd like to be able to find this in the future if I don't know what that is. Left rotation. Circular shift left. Yeah, I think that makes a bit more sense. Left shift, right shift, logical right shift, arithmetic right shift, circular shift. Yeah, I'm gonna call it circular shift left. We're gonna keep it with that. Circular shift left, because then in the future I can remember what that is. Okay, so what are we doing here? What we're doing is we have this, and then we need to look here to see what the hell they're talking about. So then we have these, the sequence of logical operations are used depending on the value of I and on the three 32-bit words B, C, and D in order to produce a 32-bit output. The following equation describes the logical functions where this is not, this is or, this is and. Man, I haven't seen that since I did proofs back in university. Yeah, okay. So, and which is why they're doing these checks here. And I could kind of cheat and just look at this, and maybe that's what I'm going to do in the interest of time, because we're already at 2.5 hours here. But I understand what's going on here. So if we're in these ranges, then this F of I, B, C, D. So WI, we know it's the word at index I. E is whatever the value of E is. This function is given by this. And then K at I is, if this is the value, then it's this, this, or this. How are they doing that? Yeah, they just hard code it. And then what's this though? What's this? This is S5 star A. Yeah, see, I would be lost because I'm not sure what that notation means. Is it just S5A? Is this just a left shift? So we did a left rotate of 1. This is A left rotate 5. Okay. Yeah, that's all it is. It's just A left rotated 5. And then you reassign the value. E is D. E is, so that's this temp value. E is whatever D was. D is whatever C is. C is B left rotate 30, right? Yep. Okay, I'm going to move this over here, and then we're just going to go off that. So what are we saying? We are saying if I is greater than or equal to 0 and I is less than or equal to 19. So if I is between 0 and 19, and then we have if I is between 20 and their ranges don't even make sense. They're saying if I is greater than or equal to 19. Yeah, they've got mistakes in here. Look at this. If I is greater than or equal to 19 and less than or equal to 0. Yeah. So they've got a few typos in here. Okay, so I'm going to look at this one. Now that I know they have typos, it kind of worries me. I don't want to fuck something up and then have to spend an hour debugging it, all because they have a typo. So I'm going to go based off of the pseudocode that we got here in Wikipedia. So if I is between 0 and 19, okay, if I is between 20 and 39, if I is between 40 and 59, if I is between, is there such a thing as not having any case? If it's between 0, 19, 20, 39, 40, 59, 60, 79, so that covers everything, right? So you don't even need this check. We know I is between 0 and 79, so if it's between 0 and 19, if it's between 20 and 39, if it's between 40 and 59, else. So what do? We're going to have a temporary no, what we're going to do is this thing is going to be, so we'll call it F is, okay, so we'll call it F We're gonna put it here just because we're gonna iterate over everything, so we might as well just do that. So F is we do B. Wait, these are bitwise. These are bitwise operations. Or this is the logical not. This is the logical or. But it's okay. B. So we do B and C, and then we OR that with not. I've actually never done not. So not B. I think that's bitwise not, and that with D, and then the K value, which I don't actually have. The K value is 5882799. So F and K. So we have F here. We have K. F is going to be B exclusive or C exclusive or D, and then K is 6 ED9 EBA1. F is B and C or B and D or C and D. K is 8F 1BB CDC. F is B exclusive or C exclusive or D. K is 0x CA62 C1D6. I'm just gonna double check that that's not binary. I'm pretty sure that's what it is. Bitwise not. Yep, that's the bitwise not. Okay. So now we have this temp value. We have this temp value. So the temp value is circular shift left. It's a left circular shift. Circular shift left. I should maybe say left circular shift. Of you take A and you shift it left by 5 plus F, which we just calculated, plus E, which we already have, plus K, which we have here, plus W at I. And then E is equal to D, D is equal to C, C is equal to circular shift left B by 30 bits. B is equal to A, and then A is equal to this temp value. And we keep doing this over and over again, and then we say H at 0 is H at 0 plus A. Yeah, I was gonna do something, try to do something fancy there, but I'm not gonna. Plus B, H2 is plus C, H3 plus D, right? Yeah, and then so we just do them in order, plus E. So we now have this here. We do this. basically just that. I'm just going to double check that these have actually matched with this one, kind of as a cross check. So we do B and C, or not B and D. And then we do B exclusive or C exclusive or D. And then we do B and C, or B and D, or B or C and D, and then we do exclusive or B, C, D. And then the K values 5A82 7999 6ED9 EBA1 8F1 BB CDC CA62 C1D6. Okay. Now, so we start with that. We determine what our F and our K are. We calculate our temp function. And then we reassign everything like this. We do that 80 times. And then we store the value in here. Now the last step we're at. When all the chunks have been processed, the message digest is represented as the 160-bit string comprised of the OR logical operator of the 5 hashed values. Not only that, holy fuck, not only that, we're taking these hash values, we're ORing them together, but we're ORing left circular shifts. So the string ABC, this is going to be the test, becomes represented by a hash value akin to a this. That's in hex. If the string changed to ABCD, for instance, the hash value would drastically be different. Okay. Okay, so we're almost there. We just need to do this last step. And this last step they have here. So yeah, it's H0 left shifted. Man, they're saying left rotate, but then here they're saying left shift. This is fucking confusing. Here they have a star 5, that's a rotation. The circular shift operation, the left shift. Now I'm confused. What are we actually doing? Right? What are we actually doing? Is this a shift or is this a left rotate, left rotate? I'm confused now. Left shift, do they mean left rotate? Or an actual left shift? Oh, okay, no. So they're doing a left shift because you take this left shift to put it into a 160-bit integer. Okay, to validate what I have, I think I'm going to need to convert what I have to a hex value. Nah, I don't really need to. I'm not going to need... there's no point of going to a hex, and then I'm going to have to convert from hex to base 64. I still don't know how I'm going to do base 64 from there. What's our time looking at? We're almost... Yeah, we should wrap this up here. So, this is only step 1, too. Just to fucking send this response with a socket, this is what it takes. Just to send this thing out, we need to do SHA-1, which we're doing now, and then we're going to have to base 64 and code that hash. Which is why I'm not sure if I should represent the message digest as a hex value, or should I just keep it as binary. What's easier to base 64 in code? I'm not sure. I think the binary is easier to base 64 in code. So this is just here. That's the thing. This is really confusing to read. This looks, because this notation that they've used the whole way throughout here is a circular left shift. But now here it's just a shift. It's just a bit shift to the left. But what's important, and then they're oriented together. Okay, they're just creating this thing. So really, it's the question is, do these values match? So what you could do is just break these things out and figure out what this number is in binary. And then just break it into pieces, because that's what you did, right? So what is this number in binary? Hex to binary. So this is the binary number. So this is the binary number. Fuck me. Okay. This is the binary number. I'm not going to do this step. I'm just going to leave it as is. I think we're going to just leave these H's as they are. And I think we're ready to test. Man, no errors here. Okay, I think we're fucking ready to test. Well, okay, there's another step here. Is we do all of this for each chunk. All of this is happening for each chunk. Right? So this would actually all be inside. So we have this. All of this would actually be inside of a loop. When are we? So all of this would be in a loop. So all that would be in a loop. All of this would be inside of a loop. So I'm going to do that. Whoa. Whoa, where did I... Hold on a second. Yeah, all this is inside of a loop. I'm just gonna put this so I can set a breakpoint, but all of this is inside of a loop, right? All of this is inside of this while loop. So we do this, we do all this, we do that. Now, is this completely right? So we'd come in, we would do all of this, and then we'd come back and we go again. While, right, we come back, do this again. Once we're done, the last chunk will be set to true. So that's when that happens. That's when we say, so while it's not the last chunk. So while it's not the last chunk, we keep going. So once this happens here, once this happens, then we come back, that'll be the end of it. So I'm just gonna set a break. I'm gonna be bold here and set a breakpoint for the end. Wow. Okay, so we got to the end. No errors on the way. Now let's take a look at H. So we have these values here of h. I'm going to compare these to, so we have h 0, 1, 2, 3, 4, and 0 represents the most significant bit. So when we looked at this guy here in binary, this is crazy. What I should do is take, so ABC should be this, but so hex 2 characters is 1 byte, so 1, 2, 3, 4. So this is 1 this is 4 bytes. That's 1 int. So I'm going to take this value and convert that to binary. So now this is what we should see. This is the number 284. This is what we should see in the most significant bit, and it's not. This is going to be the hardest part, is the debugging of this. So H0 in binary is this. So hold on a second. Let me take a look at this. Wait a minute. So this should be, so 1, 0, 1, 0, 1, 0, 1, so 1, 0, 1, 0, 1, 1, 0, 1, 0, 1. It's close, but it's actually not quite. No, it's not right. So the hash is not correct. Unless I am thinking of this wrong, I don't think I can just break this up into pieces. Okay, so this is fucking insane. It's the first, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 26, 27, 28, 29, 30, 31, 32. So 32. Well, fuck it. Let's just do this. I'll do, this is what we have. This is what we have in Visual Studio. This is what I'm expecting. How do you debug this? That's the thing. We're almost out of time. It's a shame this isn't working, because it'd be nice. This would have wrapped things up nicely. Would have just enough time to finish SHA-1 at least, and then next time we can get onto the base 64 encoding. So this looked good, right? We knew that we were getting what we were expecting up until this point. So now it's a matter of checking if I made a mistake here. From 16 to 79. A, B, C, D, E. We do 80 iterations. I'm wondering if wrapping is a problem. Wait a minute, these are unsigned integers. That could be a problem. That could be a problem. Yeah, okay. I have my own library that has my own types. So we'll just do, unsigned 32-bit integers. So if at the beginning we just say youth, right? So unsigned ints, that's fine. Unsigned ints. Man, I wish I knew how to do this in Vim, but I don't. I don't know how to do it faster than that. Okay. Do we have a different result? It's exactly the same result. Oh, but our circular shift is doing so it's wrong. It's got to end in 110, I think. Is this the same result? No, now it's a different result. Okay, let's confirm that this is all correct here. Unsigned int, unsigned int. I think this has to be an unsigned long, doesn't it? I don't think it really matters. Unsigned int, unsigned int. This is all unsigned ints. So up until this point, I think we're good. We know that that's correct. The problem is, I don't think this matters. Yeah. I don't think there's any difference. I actually, is this? Maybe if I find a I'm not sure what I could have done wrong here. It's it's pretty straightforward. This is looking the way I expected it, right? These were the values that I had. So this looked exactly as we expected. It's possible that what I'm expecting is actually not right. It could be that I'm just worried because at the beginning here it says, and wrap modulo 232 when calculating, except for ml, the like message, which is a 64-bit quantity. Wait a minute. Fuck. Does this matter? Windows is little endian, not big endian. This is all big endian. Windows is little endian. Is that... Oh man, is that what's causing this? I mean, well, I'm curious now. Shit, yeah, I'm wondering if this actually... what would the endianness matter? Well, they're saying this is in... it's just, why do they keep mentioning... would the endianness matter here? Well, yeah, when you're doing your shifts, it would, right? Yeah, this is bad. Where's that other page I have here? All constants in this pseudocode are in big endian. Within each word, the most significant byte is stored in the leftmost byte position. Yeah, but I mean, in... So the endianness could be a problem. What I'm expecting could be the problem. I don't think it is though. Yeah. Final hash value, big endian as a 160-bit number. Okay, this might have to be it for today. Yes, this may have to be it for today because I may have to leave soon. Let me just check one more thing. I don't know. I'll have to read through it again to see if there's a typo somewhere, but I think everything looks good. I don't think the endianness would matter. They keep saying that this isn't big endian, but that's just how it's stored in memory. This code would be the same if it's little or big endian, right? It's... Wait a minute, no. It would matter because I'm taking the message and putting it in to those values. It actually might matter. Okay, I'm gonna have to keep looking into this. So, yeah, I'm gonna keep looking into this to try to sort out what the issue is. And, yeah. Yeah, I'll just keep looking into this and we'll try to sort this out. Then next time will be the base 64 encoding. Yes.